about the data and the challenges imposed by the data. After that, I will talk about the experimental setup. Then I will walk you through the results obtained by the different experiments. And finally, I will talk about the key takeaways from this work and some ideas for future work. So the unknown data project is about the research data. Research data is very important for the functioning of science because they allow the comparability and reproducibility of research results. Unfortunately, there is no standard way to cite a data set in scientific text. Every researcher has his own way to put the name of the data set in his text. And sometimes it's even difficult for a human to extract that name. Like the example on the screen. Like here is the target population of TIMS. TIMS is the name of the acronym of a data set which is trends in international mathematics and science study. And before I searched about it, I didn't know that it's a data set. So it's difficult for a human sometimes to recognize the mention of data set, let it be for a machine. And the goal is to have a model that will be able to extract such mentions. And then if we extract them, we can have some like system that have them, and that system will be available for the public for any researcher who wants to search for a data set to use in his research. And to train that model, we need a data set that has text annotated with data set mentions. And such data set are like on large scale is not available. So we wanted to build our own data set. And for that, we need annotators who can read scientific papers and annotate them with the data set mentions mentioned in them. But the problem is, like, most of the scientific text does not have data set mentions. In a research paper, maybe we can find a couple of sentences that has them, and most of the text does not have them. That means that the annotators will spend most of their time reading text that does not have dataset mentions. So we want to build to have a filter to filter the text and reduce the burden from the annotators. So we want to have a model that will be given a section from a research paper, and that model will decide if it has dataset mention or not. So the task is binary classification. We have the positive class is section that contains dataset mention, and negative class sections that does not have. The main thing that we can focus on is the context of the dataset mention. And that leads us to language models. And in this work, we worked with Bert and Roberta. And our goal is to extract the sections that contains dataset mention. Like, we are not interested in the other class members. So we will focus on recall. And for the experiments, we used the Correlage dataset, which was introduced in a Kaggle competition. This dataset was introduced to bring the public attention to this problem and to let this, data scientists.
I'm sorry, Younes. I'm sorry for interrupt. Is it me, or I can see just a black, squares in the slides? Can anybody?
Yes,
because I cannot see,
Yeah, clear. There are black squares. Correct.
I don't know. Okay, I shared the screen.
I tried to read. Yeah.
Now you can see it?
There is a black square. I don't know why it comes.
Maybe if I change the mode now. Is it okay now?
Still there.
I don't know. So
can you do the presentation like this? Just make it bigger, because the black square sometimes it covers some data we are reading from the.
Okay, now is it okay like this or what?
What do you think, Dr. Abdul Hakim?
I think it's okay.
It's okay. There's the black lines, but it's okay.
I don't know where it comes from, because for me it's clear. I don't see them.
Strange.
Okay, continue, please.
Okay, so the college dataset is like the goal of it is to bring the attention of public of the how publicly funded datasets are used in research. It has 14,300 unique papers with datasets annotated in them. Some of these papers has more than one dataset mentioned, so they are repeated around 5,000. So in general, we have 20,000 papers, but the annotation is on the paper level. And we are interested on the section level. That's why we extracted the sections and we give them labels that, like, if it has this label, if the section contains the dataset mention, it's 1, otherwise it's 0. Analyzing this data that we get, we found that 88% of the sections does not have the dataset mention. So we have bias towards the negative class, and we want the model to be biased toward the positive class. So it's a difficult task. The other thing is most of the sections are long, like they cannot be fed in one piece to the language model. So for the first problem, we want to find a solution on how to feed long text into the language model. And this is the same problem that Dr. Muhammad spoke about in the morning, like how to select tokens to feed for the language model. And the other problem is class imbalance. And for that, we will use resampling and cost-sensitive learning. Like generally what we do, we have some experiments at the beginning to determine some values for the experiments. And then to make our results reliable, we run 5-fold cross-validation with the selected values. We use 80% for training and 20% for testing. And the implementation was done by using PyTorch. And the experiments run on 4 GPU each with 11 GB. We trained for 4 epochs using Adam Optimizer, and batch size 32 when we use the section content, 256 when we use the section titles. So the first problem is about the section links, like how to choose them. There is a work by Sun and Chu in 2019 in which they say, like, the best combination is to select the first the three quarters of the tokens from the beginning of the section and 1 quarter from the end. And to make sure that their results transfer to our very biased data, we run these experiments on our data using BERT, and we found that this means F510, it means that all the tokens are from the beginning of the section, and that means all the tokens are from the end of the section. And running these experiments, we found that all these 3 combinations achieved 79% recall. That means that any of them works for us, but to be in line with the previous research, which we went with this combination, and we adapted in the further experiments. And now we come to the imbalance problem. First, we tried resampling. We tried different resampling rates, and we found that the model works the best when the data is balanced. And balanced in a way that we keep the positive samples as they are, and then we reduce the negative samples to be in the same number. And we were able to get this recall value. And another way to handle imbalance is to use cost-sensitive learning. Cost-sensitive learning is to use a loss function which is biased. Here we have this function, balanced focal loss. It consists of 3 parts. The first part is alpha t, is balancing factor. It's a user-defined value, and usually it's the inverse class frequency used here. And the second part is modulating factor. This modulating factor gives weight, higher weight for difficult samples to which the model is not sure, and gives lower weight for the samples that are easy for the model. And we have gamma, this focusing parameter controls the value of this factor. And here log BT with minus, this is the cross entropy. We tried different combinations of this formula. And for example, when we put gamma is 0, then this factor doesn't exist. And when we give alpha t the same value for both classes, then it doesn't exist. We tried with this formula, different values, and we found that when alpha t is using the inverse class frequency and gamma is 4, we obtained the model works the best. With these settings, we ran 5-fold cross validation and reported on the results here. And comparing to the results of resampling, we find that it has the less effect. So resampling is better than cost-sensitive learning when it comes to this task. And we didn't achieve our results, so we went and combined the two together. And we find that with Roberta managed to achieve 83% recall. But for BERT, it was less than using resampling alone. So because BERT was sure about its predictions, which was wrong when the data is balanced. And for this, till now, we were experimenting with accuracy as the validation metric, and we were experimenting only with the section contents. Here we changed the validation metric to use recall instead of accuracy, and we also experimented with the section titles. The section, so we managed to achieve 2% improvement with Roberta with respect to recall. And with respect to titles, the best results was 70% by Roberta, which is not comparable to using contents. And that's natural because content has more context than the section titles. We went further and gave recall more weight than precision. 3 weight for recall and 1 for precision, and we improved it by 1%. And this is the final model that we managed to achieve: 86 recall with 63 precision. So the conclusion here, resampling is more effective than cost-sensitive learning when it comes to this task. We cannot depend on the section titles to decide whether a section contains dataset mention or not, although there is a tendency to mention datasets in particular sections. And the model that we have achieved is able to reduce the annotation time by more than 50% at the cost of losing 14% of the positive samples. And as a future work, we want to use this filter in our annotation task, which is happening next month. And we want to improve the tokenization process because we found that the model is not handling the acronyms correctly. For example, this acronym for a data set, it was split into 5 tokens. And we want the model to recognize it as one piece. And as also a future step, we want to build a model that is able to detect whether a text set contains dataset mention or not, and then feed it to another component that will be able to extract that mention. And that's our ultimate goal. That's it. Thank you for your attention.